Hi, this is Mr. Woodbury from College of the Sequoias. This video is for my Math 21 students. We're covering section 11.3 and we'll be talking about the two-mean test. All the data used in this video can be found in the Woodbury Math 21 StatCrunch group under section 11.3. The two-mean test is used to compare the mean of one population to the mean of another population. The two samples must be independent, meaning there's no one-to-one relationship between the values in the first sample and the second sample. If there is that sort of relationship, you should perform a paired difference test from section 11.2. An example of what a two-mean test might look like: students taking a traditional algebra class have higher exam scores than students who take the course online. We're comparing one group to another group, and there's no pairing of the data because a student in the traditional class, there's no one particular student we should match that student up with in the online class. Also, it's different from a one-mean test in that we're not saying students taking an algebra class have a mean score above 80. Right? We're not comparing a population to a number, we're comparing a population to another population. To identify this test, the claim will compare the mean of one population to the mean of another population, and you're going to need two independent sets of numerical data or two sets of summary information, including the mean, standard deviation, and size for each sample. The differences for this test, just like with the two proportion test and the paired difference test, you have to identify population 1. The null hypothesis will be mu sub 1 equals mu sub 2. The sign for h sub 1 comes from the wording in the problem. In step 3, the name of the test is the two-mean test. And to calculate this in step 4, we use stat, t-stats, two-sample, and then you select either summary or data depending on what you have. As with those other two-sample tests, we'll leave the value for the null hypothesis at 0. We'll pick the appropriate sign for h1. Next, let's talk about the conditions. Each sample has to come from a population that's normally distributed, which we can check with a QQ plot, and has no outliers, which we can check with a box plot. Or each sample has to be what we consider a large sample, 30 or greater. By the way, in this video, instead of making the QQ plot, I'm going to use the Shapiro-Wilk option. And if the p-value for the Shapiro-Wilk test is not below 0.05, that indicates that the data are normally distributed. But if the p-value is below 0.05, that tells me they are not normally distributed. Also, we still have to check that each sample size is no more than 5% of its population size. We've been checking that by multiplying the sample size by 20 and then reasoning out whether the population is bigger than that or not. Here's our first example. This is one involving summary. A random sample of 88 male deaths in a county over a one-year period had a mean age at death of 68.9 years with a standard deviation of 16.71 years. A random sample of 84 female deaths in the same county over the same one-year period had a mean age at death of 77.1 years with a standard deviation of 15.65 years. At the 0.01 level of significance, test the claim that the mean age at death in this county is lower for males than it is for females. Okay, at the 0.01 level of significance, test the claim. We know we're working with a hypothesis test here. We're comparing the mean for one population, males, to a second population, females. We have summary information for each group: sample size of 88, mean of 68.9, standard deviation of 16.71 for the males. We have the same information for females: 84 females, mean 77.1, standard deviation 15.65. Everything here says that this is going to be a two-mean test. When we label population 1, it's a good idea to select the first population mentioned in the claim. As population 1 here, we'll use males. Then we can use the sign in the claim as the sign for H1. Let's get started. Again, population 1, I'm going to select the population of males. The null hypothesis is that mu sub 1 is equal to mu sub 2. What sign will we use for H sub 1? We're going to use the less than sign, that the mean age is lower for males than females. The level of significance was 0.01, and this looks like a two-mean test. We have summary information, so the only condition we have to check is that each sample size is no more than 5% of the population size. For the males, 20 times the sample size is 20 times 88, which is 1,760 males. There are more than that. Next, for females, 20N is 20 times 84. That's 1,680 females. And again, we know there's more than that. All conditions are met, so let's go to StatCrunch and do the calculations. To perform this two-mean test with summary, press Stat, T-Stats, ToSample with summary. Sample 1 comes from the males. The mean was 68.9 years, standard deviation 16.71, sample size 88. For sample 2, females, the mean was 77.1, the sample standard deviation 15.65, the sample size was 84. Do not check the box that says pool variances. For the null hypothesis, we leave that as equal to 0. That's another way of saying that mu1 is equal to mu2. And here we're saying the mean age for men was less than women. We select the less than sign. Let's compute the test statistic and p-value. The test statistic is negative 3.32 with a p-value of 0.0005. We found that t was equal to negative 3.32. That means that our sample results were about 3 standard deviations lower than we expected, a little more than that. The p-value was 0.0005. That indicates that we should reject the null hypothesis because that is lower than the level of significance. And that means that there is sufficient evidence to conclude that H sub 1 is true. In this problem, that's that the mean age at death is lower for males than for females. Now for example 2 involving data. A golfer is considering buying a new driver. He hits 12 balls with his old driver and then 15 balls with the new driver. Here are the distances in yards. At the 0.05 level of significance, test the claim that the mean driving distance with his old driver is less than the mean driving distance with the new driver. So we're comparing the mean of one population with the old driver to the mean of another population with the new driver. Comparing two means in this fashion, this is a two-mean test. We have two sets of data here to work with. If we let population 1 be the distances with the old driver, we can then determine that the sign for H1 is going to be less than, because the claim is that the mean distance with the old driver is less than the mean with the new driver. Okay, let's start to write this up at the 0.05 level. Again, population 1 is the old driver. The null hypothesis, mu sub 1 equals mu sub 2. The alternate hypothesis, mu sub 1 is less than mu sub 2. The mean for the old driver is less than the mean for the new driver. The level of significance alpha is 0.05, and this looks like a two-mean test, but there are many conditions that we have to check. First, the sample size requirement, that the sample size is no more than 5% of the population size. For the old driver, 20 times 12 is 240, out of really an infinite number of swings that could be taken with the old driver. Same thing happens with the new. This is 20 times 15, or 300, out of an infinite number of swings that could be taken with the new driver. We still have to check that neither sample has an outlier, and also that both samples are normally distributed. We'll do that in StatCrunch with a box plot, and also by checking those Shapiro-Wilk results. Let's go to StatCrunch. The data are already in StatCrunch in the columns labeled 2-old and 2-new. To perform this test, press Stat, T-Stats, ToSample with data. Now we're going to check the conditions as we perform the test. For sample 1, the values are in 2-old, and for sample 2, 2-new. Do not check the box for pool variances. For the null hypothesis, we leave that as equal to 0. But for the alternate, we're saying that the distance for the old driver is less than the new driver, less than 0. To check the condition, scroll down to where it says optional graphs and tables. Select box plot with mean marker and also Shapiro-Wilk normality test. Press compute. On the first screen, we'll look at the Shapiro-Wilk normality test results. Both p-values are above 0.05. That means that each set of data comes from a population that's normally distributed. Next, we'll check for outliers. Here are the box plots for both the old and new driver. Notice there are no outliers, so that means that the test can be done as a two-mean test. The test statistic is negative 3.48 and the p-value 0.0011. Okay, everything checked out condition-wise. The test statistic t was negative 3.48, indicating that our sample results were about 3.5 standard deviations lower than we expected. The p-value, 0.0011. That is less than the level of significance, so we reject the null hypothesis. And that means that there is enough evidence to conclude that H1 is true. In this problem, that the mean distance for the old driver is less than the mean distance for the new driver.